In this video, I'm going to show you a simulation of the central limit theorem. So in StatCrunch, I'm going to use sampling distributions. And the first thing I'm going to do is create a uniform distribution. So StatCrunch has created here a distribution which we can see is uniform. It has a mean of 25 and a median of 25, and here's the standard deviation. So what I'm going to do is I'm going to ask StatCrunch to take samples of size 5. So I'm going to take small samples. Now, according to the central limit theorem, if we do this, and we do this repeatedly, we should not see the sampling distribution having a normal shape. So let's take a look. I'm going to have StatCrunch do it one time so you can see what it's doing. So it's taking 5 numbers from the population. You can see the 5 numbers. It's computing the mean, and then it's graphing it right here. Here, I'll have it do it again. So here are the 5 numbers, computes the mean, and it graphs it right here. Now what we'd like to do is we'd like to see what happens if we would repeat this experiment many, many times. So I'm going to have StatCrunch do it 1,000 times. And we can see that this is the result, the sampling distribution of the sample means, and this result does not have a normal shape. But according to the central limit theorem, if we increase the sample size and we made the sample size larger, again, the sample size larger would be a sample size greater than 25, we should see this distribution look much more normal. So I'm going to change the sample size from 5 to 50 and going to redo the experiment. So instead of having it do it one at a time, I'm just going to go straight to 1,000 times. And here's the sampling distribution. So you can see that the sampling distribution does have a normal shape. The mean of the sampling distribution is about the same as the mean of the population. And the spread, or the standard deviation of the sampling distribution, is equal to sigma, 14.4 in this case, divided by the square root of 50. So if you were to take a calculator and take 14.4 divided by the square root of 50, you get an answer very close to 2. Let's try it with a different shaped distribution. So this time, I'm going to create a sampling distribution that is skewed. And again, I'm going to start by taking small samples. We'll do it one time. Here are our 5 numbers. And here's the mean. We'll do it another time. Here are 5 numbers. Here's the mean. So it's going to graph the sample means here. Now what we're going to do is we're going to do this repeatedly 1,000 times. And what are we going to expect? Well, because our sample size is small, we do not expect that the sampling distribution that we'll see here in this third graph will be normal. So let's try it. Here we go. So again, here's the sampling distribution, and it does not have a normal shape. It's somewhat mound-shaped. Its mean is somewhat close to the population mean, as we can see here, but the standard deviation is quite spread out. How could we make this into a normal shape? What we need to do is take larger samples. So I'm going to change the sample size from something small, less than 25, to something large, greater than 25. So again, I'm going to use 50. Now if we do the sampling 1,000 times, what do we see? We see a sampling distribution that's very normal. The mean of the distribution is about the same as the population mean. And the standard deviation, or the spread of this sampling distribution, is the same as sigma, 11.8, divided by the square root of 50. So the population standard deviation divided by the square root of the sample size. One last graph to look at. Now, according to the central limit theorem, if we start with a sampling distribution that's normal, so I'm going to start with a bell-shaped distribution. No matter what our sample size, even if it's relatively small, something less than 25, so I'm going to create a sample of size 10. With a small sample size, because the parent population is normal, automatically the sampling distribution is going to be normal, even if we have a small sample size. So let's give that a try. We'll do it 1,000 times, and yes, we can see even though our sample size was small, the sampling distribution is normal. The mean of the sampling distribution is about the same as the mean of the parent population, and the spread of this distribution will be equal to sigma, the parent population standard deviation 5, divided by the square root of the sample size. So if you take 5 and divide it by the square root of 10, you get a value very close to 1.56. If I wanted to make this sampling distribution have even less variation, what I can do is make the sample size larger. So what if we did sample size 50 and we redid the experiment? We can see that again, we still have a normal shape, but what's different this time is that the spread of the sampling distribution is much smaller. So here we can see that the standard deviation has gone down to 0.7. If we were to increase the sample size to 500, we could make the standard deviation go down even more. Here, let's give that a try. So what if we made this to 500? We can see that our standard deviation has become much smaller than before. Now it's gone from 0.7 to 0.2. And that's a picture of the central limit theorem.